Hi, my name is Michael Otam. I'm a lecturer in plant ecology at the University of the West Indies, St Augustine in Trinidad, and I'd like to talk to you today about tropical forests and the global carbon budget. This lecture is part of the course BIOL6201, Sustainable Use and Development of Natural Resources, which is part of the Master of Science in Biodiversity Conservation run through this university. So this lecture is a background lecture in looking at how tropical forests can be used by people around the world and give a justification of why we should want to keep tropical forests around. And in particular, the service that we're looking at here is the role that tropical forests play in the global carbon budget, and therefore the role that tropical forests play in mitigating, preventing global climate change, which is going to be a problem in the future of the world. So, what I want to talk about today is, first of all, the global carbon budget. What is the global carbon budget? Why should we care about the global carbon budget? I want to talk about terrestrial carbon pools in particular, because it is the terrestrial carbon pools which tropical forests make up. And terrestrial carbon pools are also the pools which humans tend to influence the most, and therefore which we can influence then, and therefore influence global climate change. I want to talk about carbon movement between different carbon pools, mainly between the terrestrial carbon pools and the atmospheric pools, because you probably know it's the atmospheric pool which drives global climate change by trapping more heat in the atmosphere and therefore heating up the atmosphere over time. I want to take a look at how that carbon transfer between the terrestrial carbon pools and the atmospheric pool are being influenced by modern day drivers or changes in time. And finally, I want to take a look at global climate change and the global climate budget and the role that tropical forest has to play in that. Okay. So first of all, the global carbon climate budget. Global carbon budget. Right, you've probably seen a diagram like this before. Let me just break it down more in words first of all, and then we'll go back to that diagram there. The main pools of carbon on the Earth are in carbonate rocks, fossil fuel reservoirs, terrestrial ecosystems, oceans, and in the atmosphere. And you can see the relative numbers of carbon which are found in each of these different pools. So carbon exists in a state which is contained within these different reservoirs. So carbonate rocks with 65 million gigatons is obviously the largest pool of carbon on Earth. The oceans are the second largest, a lot of carbon dissolved in those oceans, and fossil fuel reservoirs next highest, and terrestrial ecosystems come in, what's that, fourth, and finally atmospheric carbon. Now, our terrestrial ecosystems are our main focus because they are the ones which tend to be changing and exchanging carbon with the atmosphere. Oceans are also very important, and there may be big issues with this deep ocean carbon pool in the future if global oceanic currents change and maybe bring more carbon to the surface, which can then interact with the atmospheric carbon pool and drive that up. But for now, we're concentrating in this lecture on the terrestrial ecosystem pools. And as you can see, that the terrestrial ecosystem carbon pools are in vegetation and in soils and detritus. And globally, the vast majority of the global carbons is in soil and detritus, with a fairly substantial amount in vegetation. This proportion varies in different parts of the world, as we will see. So diagrammatically, we can see that we have vegetation, about 500 gigatons, 2,000 gigatons in soil and detritus, for a total of 2,500. And this diagram also shows some of the fluxes that we get between the different carbon pools. So we get a release of carbon from terrestrial ecosystems into the atmosphere, and these are returned back into the terrestrial ecosystems by photosynthesis and uptake, and also respiration of these terrestrial ecosystems also puts a lot of carbon back into the atmosphere. But we'll talk more about that in a minute. A couple of the other things to note on here: I didn't realize so much carbon went in from terrestrial ecosystems into the atmosphere through fossil fuel and cement production. Cement production is a huge contributor of carbon to the atmosphere. And here we have the cycling in the marine ecosystems, which we're not going to worry about too much. Okay, so we saw that. Right, so concentrating or zooming in on the terrestrial carbon pools, we have the majority of the terrestrial carbon pools are from the forests. So forests contain the vast amount of carbon in the terrestrial carbon pools. And we can break those forests down into three main types: boreal forests, temperate forests, and tropical forests. Tropical forests hold the largest amount of terrestrial carbon at 471 gigatons, and this data is from et al. 2011. I will put this reference up on My Learning if it's not already the My Learning page for this course. Boreal forests, because of their extent, also have a substantial amount of terrestrial carbon. Much less of it is contained in the biomass compared to tropical forests, and more is contained in soil and litter detritus, and this reflects the adverse nature of the climate in the boreal region, which mitigates against primary productivity, and therefore less carbon is held actually in the biomass compared to tropical forests, where the proportion is much higher. And in fact, over half of the carbon in the tropical forest pool of carbon is in the biomass, much less is in soil and litter detritus. And I think this lesser amount of carbon in temperate forests is more reflected by its more limited extent compared to boreal forests and tropical forests. Okay, now the thing that we're interested in when we talk about global climate change and how tropical forests fit in, and forests in general fit into global climate change, is how carbon moves between these different pools. And if we look at Pan et al. 2011, which is this particular article from Science, a large and persistent carbon sink in the world's forest, we can see that boreal forests are acting as a net sink from 1990 to 2007. Temperate forests are also acting as a net sink, and tropical forests are also taking up larger amounts of carbon than the other two combined. But unfortunately, this sink represented by tropical forests is balanced by tropical forest deforestation emissions. and that the amount of emissions which are result from tropical deforestation almost exactly balances the amount which is actually taken up by tropical forests, and that reduces the effectiveness of tropical forest and indeed world forests as a carbon sink. We're actually trying to get carbon out of the atmosphere and reduce the impacts of global warming. So reduction of tropical forest emissions is one of the major ways of increasing tropical forest sinks and therefore reducing the amount of carbon in the atmosphere, and so decreasing the amount of global warming or the impact of global warming. So this kind of thinking is one of the main types of thinking behind the initiatives to try and prevent tropical forest deforestation, because once you slow down tropical forest deforestation, you will slow down these emissions and then allow the sink to operate unhindered, as it were, and so actually pull carbon out of the atmosphere. So some of the modern day drivers of carbon fluxes around the world are, first of all, natural processes would be carbon fertilization. So sink properties of tropical forests seem to be increasing. So intact tropical forests are actually taking up more carbon these days than they were in the past, and this has been called a carbon fertilization effect. And what this means is that as the amount of CO2 in the atmosphere increases, then there is an increase in the rate of photosynthesis. Photosynthesis effectively becomes more efficient, so you will tend to get a greater productivity, and a greater productivity means a greater amount of carbon being pulled out of the atmosphere, moving from the atmosphere into the biosphere. And this appears to be happening all around the world, not only in tropical forests but also in temperate and boreal forests as well. In addition to temperate and boreal forests are also benefiting from changes in land use by humans. In the past, agriculture has been much more broad scale, and it tended to clear large areas of forest. But largely these areas have been abandoned from agriculture as agriculture becomes more efficient in more smaller areas, and forests can recolonize former agricultural areas. And this is happening a lot in Europe, Northern and Eastern Europe, and in North America. So temperate and boreal forests are taking up more carbon as they expand back into areas of their former range. However, human-induced deforestation in tropical forests is on the negative side. It is behind the main release of carbon from terrestrial ecosystems back into the atmosphere. So human reduction in the area of tropical forests is one of the main reasons why carbon is increasing in the atmosphere. And if we can slow down or stop this deforestation, we can actually see that there is going to be a net sink of the forest will act as a net sink of carbon and actually pull carbon from the atmosphere and mitigate against global warming through buildup of carbon. Right, so next slide. So yeah, carbon fertilization, which we talked about. There is some evidence of carbon fertilization occurring. Looking at permanent plot studies in tropical forests and elsewhere, we can see that the amount of productivity, the net primary productivity, is actually increasing, and the biomass is increasing in tropical forests. Longer growing seasons in boreal and temperate forests means that there is increased productivity, and therefore net increases in biomass and transfer of carbon from the atmosphere into the biomass. There is no effect of increased growing season in the tropics, however, mainly because net primary productivity does not tend to be limited by temperatures in the tropics. So if you increase your temperatures, you're not going to increase your growing season, and you're not going to increase your net primary productivity. So this increase in growing seasons doesn't occur in the tropics, first of all, so it has no effect on increasing the biomass, increasing the primary productivity. Another major issue with increased temperatures globally is increases in respiration rates. So ecosystems are in a balance. You will get carbon pulled from the atmosphere through photosynthesis, but at the same time those ecosystems will also be respiring, using up the carbon which has been pulled in through photosynthesis. Organisms and trees themselves will be respiring, using up these carbohydrates and releasing the carbon back into the atmosphere. Now, the rate at which respiration goes is dependent a lot on temperature, because respiration is effectively a chemical reaction, and chemical reactions will go faster if the temperature is higher. So respiration rates will tend to be higher as global temperatures increase. So this means that respiration rates are higher, there is a greater amount of carbon being transferred into the atmosphere through respiration. And some of the main factors behind that is greater microbial activity and release of carbon in breakdown of soil litter and carbon in the soil. As we saw in previous slides, a large proportion of carbon in terrestrial ecosystems is in leaf litter and in soil. And what mediates the transfer of carbon from this pool into the atmosphere is respiration of microbes as they break down this, what is for them a food source. If you increase the amount of temperature, then you're going to increase the amount of respiration and therefore the amount of transfer of carbon from this pool back into the atmosphere. Sorry about all the background noise. Maybe one day we can afford a soundproof room and you won't have to worry about this. So increased temperatures is going to mean that we get more transfer of carbon from soil into and leaf litter into the atmosphere. And this is going to impact all forest types, particularly temperate and boreal forests where temperature is a constraint. There will be longer periods of time where respiration is going to be high in these types of forests. Tropical forests will also be impacted. It only takes a slight increase in temperature and the amount of respiration is going to increase dramatically. This increase in respiration is a big problem. Because individual trees and ecosystems are in somewhat of a carbon balance, so if they can pull in more or as much carbon through photosynthesis, through their net primary productivity, to balance the outputs through respiration, the biomass will remain constant and everything will be fine. But if the respiration rates increase above that net primary productivity, then the ecosystem and an individual tree are going to be living on borrowed time. They cannot sustain this unequal balance in the amount of carbon outputs and inputs, and they will need to try and reduce their biomass and therefore reduce their respiration load to try and come back into balance and maintain themselves. Okay? And this process will be exacerbated through drier weather. And many of the global climate models now predict longer dry seasons or significant dry periods for tropical forests. And what that will mean is that trees will have to spend more time with their stomata closed to prevent desiccation. And because they close their stomata to prevent water loss and desiccation, they cannot photosynthesize. So that will further decrease the net primary productivity and make individual trees and tropical ecosystems more vulnerable then to unsustainable rises in respiration rates. So at some point, the temperature and the respiration rates are going to rise to a certain point, and the amount of rainfall is going to fall below a certain critical point where large numbers of species in tropical forests will not be able to survive. They will not be able to have a positive carbon balance, and therefore large numbers of individuals of these species will begin to die off. Okay? And this will create, if it's large enough, we will create a massive change in tropical forests. The only species which will survive will be the ones which can survive the water deficit, and these may be the more deciduous forest species. So wet tropical forests will revert to dry forests, they will convert to dry forests and savannas, and there will be a massive die-off of susceptible species. So when you get a massive die-off of individuals in tropical forests, that is going to mean that there's going to be a massive spike in the amount of dead organic matter in these forests. And this massive spike in dead organic matter is going to mean a greater amount of decomposer activity. A greater amount of decomposer activity with higher temperatures as well will mean a massive increase in carbon in the atmosphere through respiration. So this is going to feed again into increasing carbon in the atmosphere and create a bit of a feed-forward loop in increasing temperatures, increasing respiration, changing rainfall cycles, and therefore make greater losses of tropical forests more likely. We can also include drying out because of dry periods and deciduousness, making tropical forests much more vulnerable to fire. Humans love their fire, and if you have a forest which is dry and vulnerable to fire, more often than not human activities will provide some sort of ignition source which is going to burn out that forest. So drier forests will become much more vulnerable to destruction from human activities. So deforestation rates will also increase, and therefore more carbon will be released into the atmosphere, creating more of a buildup of carbon in the atmosphere, and then greater global warming and so forth with that feed-forward loop. So collapse of tropical forests, a sudden crossing of a threshold and a massive die-off of species will lead to a massive increase in carbon in the atmosphere, as that large pool of carbon in the tropical terrestrial forests, about 250 gigatons, will lead to an increase of carbon in the atmosphere with increased temperatures, which will lead to increased respiration and further stress on terrestrial forests, and therefore release of carbon. And what scientists fear is a feedback loop will be set up, leading to runaway global warming. And we don't want that to happen. So going back there to the roles, in summary now, the role which global tropical forests and global forests all around the world play in the global carbon budget and in restraining global climate change and heating up, or global warming, heating up of the atmosphere. Tropical forests play a big role in this. They are one of the biggest sinks of carbon, removing carbon from the atmosphere. And if we lose our tropical forests, then we are going to lose that big sink, and that may create unsustainable or runaway global warming, which would have devastating consequences for human societies around the world. So the best way to try and stop that global climate change and reduce the risk of runaway global warming is to try and conserve our tropical forests. So in my next lecture I'm going to talk about how policies have been trying to set up to try and reduce that amount of tropical deforestation and so conserve the services of carbon sequestration that these forests give to us. Okay, thank you very much. I will see you in the next lecture.